Hello students, in this video I'll be explaining about an important theorem called as sampling theorem, and in the later part of the video I'll explain the proof of sampling theorem using Fourier transform. So the sampling theorem is a powerful theorem which is used heavily in signal processing, especially for digital communication systems. So in order to understand the sampling theorem, you need to understand about a signal called as band limited signal. So let's consider a continuous time signal x of t, and this signal is a band limited signal, which means that the frequency component or the frequency spectrum is limited in a particular range. So for a band limited signal, if you take the Fourier transform, the frequency spectrum x of j omega, this will be 0 for those omegas, those frequencies which is greater than or equal to omega m. So omega m is called as highest frequency component. So omega m is highest frequency component of this signal. Okay, so for those frequencies above this highest frequency component, the Fourier transform is 0. If that is the case, then that signal is called as band limited signal. And sampling theorem is applicable for band limited signal with highest frequency component denoted by omega m radians per second. So for example, if we consider a signal, a band limited signal with highest frequency component, the magnitude spectrum will be something like this. So I am trying to plot the magnitude spectrum of a band limited signal. So on the y-axis we have the magnitude of Fourier transform. So this is x of j omega, which is the magnitude of Fourier transform, and in the y-axis, in the x-axis we have omega in radians per second. So for band limited signal, as I mentioned previously, there exists a quantity called as omega m, which is the highest frequency component. It is there in the positive side as well as on the negative side. The reason is we have taken the modulus of omega. So for those frequencies above this omega m, the above the maximum, the highest frequency component, the frequency spectrum or the Fourier transform will be 0. So there is no signal above omega m, and below this minus omega m, and there can be some signal in between this minus omega m to plus omega m. So for example, I'm drawing a signal something like this. So it need not be necessarily like this. It can be any signal between minus omega m to plus omega m. But one thing is certain for a band limited signal is that for frequencies above this omega m, the Fourier transform is 0. That means there is no signal with frequency component above omega m. And sampling theorem is applicable for those signals which are band limited with the highest frequency component being omega m. So just to recap, omega m is in radians per second. In hertz we have fm. So the highest frequency component in hertz is equal to omega m divided by 2 pi. So fm is the highest frequency component of the given band limited signal. Now let me give the theorem. So the theorem states that for a band limited signal xt, with highest frequency component being fm, for a band limited signal xt with highest frequency component fm, this signal can be reconstructed. So this signal can be reconstructed from its samples if the sampling frequency, so let me denote the sampling frequency by Fs, is at least twice Fm. Okay, so analytically we can write the condition something like this. We require the sampling frequency to be at least twice the highest frequency component of the signal. Okay, so this is sampling theorem. So we know that we can get the samples of the signal by sampling the signal at some particular sampling period, let's say t. So if we have a signal, so I am drawing a random signal. So this is x of t with respect to t. So if we are sampling the signal with a sampling period of capital T, so this is small t. Okay. So if we are sampling the signal with a sampling period of capital T, so it is like switching. I mean switching at a period of capital T. Okay. So something like this. So if we use a switch which closes at every capital T time, and suppose here you are giving x of t. So after each capital T, this switch closes and the signal will be reaching here. So on this end you will get the sampled signal, which is denoted by xst. Okay, so what will be this sampled signal? So this sampled signal, which will be samples at a period of capital T. So this will be something like this. So if it is this is capital T. Suppose the gap between the samples is capital T. So I am trying to get the samples after each t. So this is t, this is 2t, this is 3t, 4t, and so on. Similarly, on the left side you have minus t, minus 2t, and so on. Okay, so this capital T is called as sampling period. So it is the period at which we are sampling the signal, and I have defined something like Fs as sampling frequency. So sampling frequency is nothing but 1 by capital T, which is sampling frequency. So the question the one of the key question that we need to address is what can be a good sampling period? What is a good sampling period? Can we have a high sampling period or a low sampling period, and which sampling period to be selected? So sampling theorem says that you need to select the sampling period in such a way that the sampling frequency must be at least twice the highest frequency component in that signal. Okay, so you will be able to recover the original signal only if you select the sampling period in such a way that the sampling frequency, so sampling frequency is nothing but 1 by t. So 1 by t equal to Fs need to be greater than or equal to twice Fm. So Fm is the highest frequency component. So this is sampling theorem, and so now we will come into the proof of sampling theorem. So in order to prove sampling theorem, we need to understand few more concepts before going into the proof of sampling theorem. So one such concept is, so first I will explain that concept, and there are one more concept. So I will explain those two concepts, and then we will come into the proof of sampling theorem. So the first concept is sampled signal. So sampled signal, which I have denoted it by x s of t, uh, s of t, the sample signal is obtained using impulse train sampling. So I'll explain what is this impulse train sampling. So in the previous page, I have used a switch to uh, to uh, to separate or to get the sampled signal from the original signal. So this closing of the switch after each time period, each sampling period, capital T, can be thought of as impulse train. So I'll draw and I'll try to explain it further. So if we have a signal x of t here, and we are going to multiply that with something called as impulse train. So this is impulse train. So what is impulse train? So impulse train is a train of impulses. So uh, this is at t is equal to 0. At capital T we have another impulse. At 2t we have another impulse. At 3t we have another impulse, and so on. Similarly to the left side as well. This is minus t, this is minus 2t, and so on. So this is an impulse train. Okay, so if we have a continuous time signal, so if we have a continuous time signal something like this, you are multiplying this signal with this impulse train, so that you will get the sampled signal. So output of this will be the sampled signal x s of t, which is actually x of t multiplied by this impulse train. So let me denote this impulse train as del of t with suffix being capital T. Remember, del of t is representing impulse signal, which is just this at t is equal to 0. Now I am denoting an impulse train with the sampling period capital T. So so what it means is, it is actually a train of impulses. It is not just the impulse at t is equal to 0, but you have impulses at t is equal to capital T, t is equal to 2t, and so on. So if this capital T is small, these impulses will come closer. Okay, so I am denoting this impulse train by del t with suffix capital T. So the sampled signal x s of t is equal to x of t multiplied by del of t with suffix capital T. Okay, so this is one of the important concept. A sample signal can be obtained by using impulse train sampling. Okay, or we are sampling the signal using an impulse train of impulses, which is denoted by del t of t. Now, what is this del t of t exactly? So this del t of t can be written as, so we know that there is a unit impulse is there, right? So the middle one is actually the unit impulse. So I am writing it as del of t. And what is this? The impulse at t. So this is nothing but del of t minus capital T. So you have plus del of t minus capital T. The next one at 2t is plus del of t minus 2t, and so on, plus etc. And towards the left side, the impulse at minus t corresponds to del of t plus capital T, and so on. Okay, so in general I can write this impulse train as del of t with suffix capital T. This is nothing but summation. So I am writing del of t minus k capital T. K is ranging from minus infinity to plus infinity. Okay, so this is an important concept. The impulse train is actually a train of impulses at 0, t, 2t, 3t, etc. can be represented as summation k is equal to minus infinity to infinity del of t minus kt. So when k is equal to 0, it corresponds to impulse at 0. When k is equal to 1, it corresponds to impulse at capital T. K is equal to 2, it corresponds to impulse at 2t. K is equal to or minus 1, it corresponds to impulse at minus t, and so on. So this impulse train is denoted by del t of capital T, which is summation del t minus kt. Okay, so this is one thing that you need to understand. A sampled signal x s of t is obtained using a train of impulses. Okay, so another thing that you need to understand is this is the critical step, is finding the Fourier transform of the impulse, the sampled signal. Okay, so second thing that you need to understand is finding Fourier transform of sampled signal. So we will use these two concepts to prove the sampling theorem. So finding the Fourier transform of sampled signal. So sampled signal is denoted by x s of t. Okay, so first I'll write what is that Fourier transform. Okay, so so uh, so I'll once again write what is x s of t. X s of t is the sampled signal, which is nothing but x of t multiplied by del of t with suffix capital T, or in other words, it is x of t. This is actually summation k is equal to minus infinity to infinity del of t minus k capital T, right? So this is the sampled signal. Now the question is, what is the Fourier transform of this? What is the Fourier transform of this sampled signal? So first I'll give the Fourier transform, and then I'll try to derive the Fourier transform. So the Fourier transform, so I'll write it in a big uh, letters. So Fourier transform of x of t is actually, it is 1 by capital T summation k is equal to minus infinity to infinity x of j omega minus omega s. So Fourier transform of the sampled signal is given by 1 by capital T summation k is equal to minus infinity to plus infinity x of j omega minus omega s. So first let's try to understand what is this Fourier transform means. So remember that the Fourier transform of x of t is Fourier transform of x of t. We have taken this x of t as a band limited signal, and the band limited signal with highest frequency component being omega m. So the Fourier transform, we have denoted it by x of j omega, right? So now we are talking about the Fourier transform of the sampled signal, which is equal to 1 by capital T summation k is equal to minus infinity to infinity, the same x, which is the Fourier transform of x of t times j into omega minus omega s. So this is actually what this is actually a Fourier transform which is shifted by omega s units. So where this omega s is the sampling frequency, which is obtained by 2 pi by t. Okay, so we will come back into the explanation of this Fourier transform later. Before going into that, we'll try to derive this Fourier transform, or how did we get the Fourier transform of sampled signal as 1 by capital T summation k is equal to minus infinity to infinity x of j omega minus omega s. So it is very important to understand this Fourier transform. So So let me try to explain the problem at hand once again. So if we have the signal x of st, which is x of t multiplied by summation k is equal to minus infinity to infinity del of t minus kt. If this is the signal, what is the Fourier transform of x s of t? Okay, so in order to find the Fourier transform, what we'll do is we'll try to find the Fourier series expansion of this term. So what we'll try to do is we'll try to find the Fourier series, in particular the exponential form Fourier series expansion. Okay, so we are trying to find the exponential form. So I'll write that as well, exponential form Fourier series expansion. So we can apply Fourier series for this impulse train. The reason is it is a periodic signal. So remember that the Fourier series exists for periodic signal, and this impulse train, if you look at the figure of impulse train, we can see that it is a periodic signal with period being capital T. So the angular frequency omega s, we have denoted it by omega s as 2 pi by capital T. Since it is a periodic signal, there exists a Fourier series, and so let me try to write the Fourier series. So I'll denote this as del t with the suffix capital T. It is the same thing. So the exponential form Fourier series is del t capital T is equal to, the exponential form Fourier series says that summation ck from k varying from minus infinity to infinity e raised to j k, here frequency is omega s t, right? So this is the exponential form Fourier series of del t capital T. Now what is the ck? Ck by Fourier series coefficients expression, it is 1 by t integral over a time period, right? So let me draw the impulse train. So at t is equal to 0, we have an impulse. At t is equal to capital T, we have another impulse. At t equal to 2t, we have impulse, and so on. Similarly, to the left side, minus t, we have an impulse. At minus 2t, we have an impulse. So this is del of t suffix capital T, right? Fine. So what is the ck? Ck is 1 by capital T integral over a time period. So for convenience, let's take the period as from minus t by 2 to plus t by 2. So that forms a period, right? So integral minus t by 2 to plus t by 2 del t of del t capital T e raised to minus j k omega s t dt. Okay, so this is the expression for finding the Fourier series coefficient. So please remember these equations. These are the exponential form Fourier series expansion. So I have elaborated the impulse train as exponential form Fourier series, and the coefficient ck is found as 1 by t integral of minus t by 2 to t by 2 del t of t e raised to minus jk omega s t. Now, what is this? What is the signal from minus t by 2 to t del t of t? So from minus, so this is important. From minus t by 2 to t by 2 del t of t. So del t of t is the impulse train, but for the range from minus t by 2 to t by 2, it is just the unit impulse, right? So I can write this as 1 by t integral minus t by 2 to t by 2 del of t, because for that range it is just the impulse signal e raised to minus j k omega s t dt. Okay, now what is this integral? Integral from minus t by 2 to t by 2 del of t e raised to minus jk omega s t is equal to, you put t is equal to 0, so t equal to, t becomes 0, so this t equal to 0, and hence this e raised to becomes 1. Okay, and integral of minus t by 2 to t by 2 del t, the whole thing turns out to become 1. Right, so if there is any doubt, you can ask me to elaborate. So this ck turns out to be 1 by t. Okay, so if this ck is 1 by t, what is del t of del capital T of t? So this ck, we have found it as 1 by capital T. Okay, so let me write it in a fresh page. Del capital T, which is the impulse train, is nothing but 1 by capital T. So let's go back to the previous page. Ck is 1 by capital T. Summation k is equal to, minus infinity to infinity e raised to j k omega s t. E raised to j k omega s t. Okay, so we have obtained the uh, the Fourier series, actually the complex exponential form Fourier series expansion of del t capital T. Okay, so now let's try to substitute that in the in the sampled signal. Okay, so we have obtained as this as 1 by capital T summation e raised to j k omega s t. Okay, so let me try to rewrite x s of t, the sampled signal, as x of t multiplied by this signal, right, which is 1 by t summation k is equal to minus infinity to infinity e raised to j k omega s t. Okay, so I'm just rewriting that for I'm taking 1 by t on the left side, x of t inside the summation, so it becomes 1 by t summation k is equal to minus infinity to infinity e raised to j k omega s t into x of t. So this is the sampled signal now. Okay, so now we are in a position to take the Fourier transform. So I am now applying the Fourier transform on the left side as well as right side. So I am taking the Fourier transform of this, and on the right side I am applying the Fourier transform. So 1 by t is a constant, so I am applying a Fourier transform on this. Okay, so now you need to recollect one property. So while telling about a property, I told that this property will be used in the proof of sampling theorem. So it is the frequency shifting property. So if you multiply a signal with e raised to j k omega s t, then the Fourier transform will be shifted, right? So on the left hand side we have the Fourier transform of x of s is nothing but x s of j omega, which is equal to 1 by t summation k is equal to minus infinity to infinity. The Fourier transform of x of t is x of j omega, so it is x of j. Now it is being shifted by omega minus k omega s. Okay, so multiplying x of t with e raised to j k omega s t by frequency shifting property, it is x of j omega minus k omega s. Okay, so this is what we were trying to derive. The Fourier transform of sampled signal is x s of j omega equal to 1 by t summation k is equal to minus infinity to infinity x of j omega minus k omega s. So I'll quickly write the two things that we have understood. So we have understood that the sampled signal x s of t. So this is the first thing that we have understood. X s of t is written as x of t multiplied by summation the impulse train k is equal to minus infinity to infinity del of t minus k capital T, where capital T is the sampling period. This is the first thing that we understood. Second thing is the Fourier transform of the sampled signal xs of j omega is nothing but 1 by capital T summation. It is summation k is equal to minus infinity to infinity x of j omega minus k omega s, where this omega s is the sampling frequency, which is equal to 2 pi by capital T, or it's equal to 2 pi fs. Okay. So these are the two things that we understood. Now let's come to the proof of sampling theorem. So with these two concepts, I'll quickly write the first thing. The first thing is we have obtained the sample signal xs of t as x of t multiplied by uh, summation del of t minus kt, the impulse train. K is ranging from minus infinity to infinity, and I've taken the Fourier transform of this. This is xs of j omega is 1 by capital T summation k is equal to minus infinity to infinity x of j omega minus k omega s. So I am repeating this multiple times so that you'll be comfortable with what I am explaining. Okay, now let's try to understand further what is this. What is the Fourier transform of sampled signal? So if I am expanding this summation, so I am writing the summation once again, xs of j omega. So there is 1 by t, which is common. So now I am trying to expand this expansion with first we will put k is equal to 0. So k is equal to 0 is something like k is equal to 0 means this term becomes 0. So it becomes x of j omega. So what is this x of j omega? X of j omega is the Fourier transform of, okay, so I'll write here. So x of j omega, this is actually the Fourier transform of the band limited signal x of t with the highest frequency component being omega m. Okay, so this is the Fourier transform of x of t. Now what is the summation when k is equal to 1? So when k is equal to 1, it is x of j omega minus omega s. Okay, so this is actually the Fourier transform of the signal x of t, which is shifted by omega s. Okay, so we'll draw that now. At that time it will be clear. So this will be a signal which is actually delayed by omega s units. Similarly, you can write for k is equal to 2 3 etc plus etc, and towards the left side, if k is equal to minus 1, what it will become? It will become x of j omega plus omega s. Okay, so this is what this is actually the Fourier transform of the signal, which is shifted to the left or advanced by omega s unit, and the rest of the components will continue on the left side. Okay, so now let's try to draw x of j omega, x of j omega minus omega s, and x of j omega plus omega s, and the remaining components are there. So now let's try to focus on these three components. So first I'll draw the Fourier transform of the signal. So in the first page, I have explained that it is a band limited signal. So you have omega m here, and left side also we have minus omega m, and the signal will be between these two omega m's, because it is a band limited signal. So this is so I have taken it as 1. So what is this? This is x of j omega, the first thing. Now secondly, now I am trying to plot the Fourier transform of the sampled signal. So this is important to understand. So this is the Fourier transform of the signal. Now I am trying to draw, what I am trying to draw is xs of j omega. Okay, so what is xs of j omega? It is 1 by t times summation of these infinite terms. Okay, what are these infinite terms? So let's try to take these three terms alone. So what is this term? This is x of j omega itself. And what is the second term? So this term is x of j omega, which is shifted by omega s, and on the left hand side we have x of j omega, which is shifted to the left by omega s. Okay, so first I'll draw this x of j omega itself. So x of j omega is a band limited signal, as we seen previously. It has minus omega m, it has plus omega m, and the signal is something like this. There is one difference. The peak is now, it is not 1, but it is just 1 by t. The reason is we have a 1 by t multiplier. So this is x of j omega. Now what is the next signal? So this is the important thing. The next signal which corresponds to this part, x of j omega minus omega s, is, suppose omega s is somewhere over here. Okay, so I am taking randomly here. This is not random. So omega s is obtained from capital T, right? Omega is equal to 2 pi by t. So once you fix the sampling period, omega s will be finalized. So from that you will get omega s. Okay, so if this is omega s, and what will be the second signal? This will be a Fourier transform x of j omega, which is shifted by omega s. Okay, so now I am trying to draw, this is omega s. So on the left hand side you will have omega s minus omega m, and on the right side somewhere over here this is omega s plus omega m. And the signal here in this range, so this height will be 1 by t. So this will be the signal corresponding to x of j omega minus omega s. Okay, and similarly on the left hand side, suppose this is minus omega s, this is minus omega s plus omega m, and on the left hand side somewhere over here you have minus omega s minus omega m, and this is 1 by t. So this will be the signal, x of j omega plus omega s, and this is the signal x of j omega minus omega s. Okay, so here I have drawn it, the omega s towards more towards the right, and here also the omega s is more towards the left. So I have drawn this like this intentionally, so that there is a gap between these two quantities. So here is the critical part. So you need to understand this part very, very well to understand the sampling theorem. So if we choose this omega s, so this omega s is in our hands. Why? We can decide this omega s because this t is in our hands. We can choose, we can decide the sampling period. Depending upon the choice of the sampling period, omega s will be varying. So if t is a small quantity, omega s will be high. If t is small, if t is a very small quantity, that means we are sampling at very, very, very near interval, what will be this omega s? The omega s will be high, and hence it will be more towards the right and more towards the left in this side. In that case, there will be a gap between this omega m and omega s minus omega m. So the importance of this gap is, this is the frequency spectrum or the Fourier transform of the sampled signal. And if we have a signal something like this, it is very easy to separate out the original signal. Okay, so if we have a Fourier transform or a frequency spectrum something like this, it is very easy to separate out the original signal. So in order to separate out, you just need to use a low pass filter. So this is an important concept that you need to understand. So if you use a low pass filter, something like this, so low pass filter is a filter which passes low frequency components and blocks the high frequency component. So if you use a low pass filter, it will filter out the higher frequency component, and you will be able to obtain the required original low frequency component. Okay, so if you use a low pass filter, you will get you can recover or you can reconstruct the original signal. Okay, this is not the case if you choose a high value of capital T. So this is the concept that you need to understand. If you choose a high value of capital T, suppose you have chosen a very high value of capital T. Very high value of capital T means what? You are sampling at very slow rate. That means you are sampling now, then you wait for some time, and then you are sampling. So capital T is very high. If capital T is very high, what happens to omega s? This omega s becomes very small. Okay, so if this omega s becomes very small, what will happen is this omega s will come somewhere over here. So I'll try to draw that as well. So this is the frequency spectrum of the sampled signal x s of j omega, and this is, here you have omega m 1 by t. This is plus omega m, this is omega m, this is minus omega m. And suppose I am choosing a high capital T such that omega s is small. Okay, so suppose I am choosing this omega s as somewhere over here. Okay, instead of a high omega s, suppose I am choosing an omega s somewhere over here. So minus omega s is somewhere over here. Okay, so what is x of j? Omega minus omega s and omega plus omega s in this particular case. You will see that, so this point will be omega s minus omega m, and somewhere over here you will have omega s plus omega m. And what happens to the frequency spectrum? The frequency spectrum overlaps, right? So this is 1 by t, but here the frequencies get overlapped. The high frequency component of this region get overlapped with the frequency component of x of j omega minus omega s. Similarly, on the left side also the frequencies signals get overlapped. So these signals get overlapped here. And because of that, even if you use a low pass filter, to try to get the original signal, you will not be able to get the original signal. There will be some distortion due to this high frequency component as well. So even if you use a low pass filter, these components will also come into the picture. Okay, and this problem is called as the problem of aliasing. So this problem of overlapping the frequency components because of not satisfying the sampling theorem condition is called as the problem of aliasing. Okay, so now we are left with the final thing, the condition for sampling theorem. So from this figure we can see that the condition is that we require this omega s minus omega m to be greater than or equal to omega m. Okay, so the condition is we require, so this is the final thing, omega s minus omega m to be greater than or equal to omega m, right? So we require this point to be towards the right of omega m. So omega s minus omega m need to be greater than omega m, which means that the sampling frequency must be at least twice that of omega m. And this is the sampling theorem. So we require the sampling frequency to be at least twice that of the highest frequency component omega m. So similarly in hertz we can write, so it will be 2 pi omega fs. So 2 pi fs is greater than 2 into 2 pi fm. in by cancelling 2 pi, we can write we require fs, which is sampling frequency, to be at least greater than twice the highest frequency component in that signal. Okay, so the question of how to choose a sampling period is being answered here. So what is the answer? So I'll write the question: how to choose the sampling period capital T. So what you need to do is, if you are given with a signal which is band limited by highest frequency component omega m or fm, you need to, by sampling theorem, you need to have a sampling frequency which is at least twice that of the highest frequency component, and hence we can write this fs as 1 by t. So we require this 1 by t to be greater than or equal to twice fm, or you can write this t as less than or equal to 1 by 2 fm. So you select a sampling period which is less than or equal to 1 by 2 fm. Okay, so this is sampling theorem, and this is how we will prove the sampling theorem. So I'm not explaining it once again. So you need to understand these two concepts: finding first thing is sampled signal as impulse train sampling, and second thing is finding the Fourier transform of the sampled signal. So these two concepts are required to prove the sampling theorem. So I hope it is clear for you. Thank you.